Okay, so in the previous class, we looked at classification in some detail. And towards the end, we trained a simple logistic regression model. All right. And for that, we used the Autograd library in Pytorch. Right. So we didn't manually compute the gradients ourselves. We let Pytorch compute the gradients and use that to do gradient descent. Yeah.
This Autograd,
Yeah.
when Pytorch do some approximation that, like when we were doing auto differentiation part, auto differentiation was straightforward, just change.
Correct. Yes.
Does this Autograd do some kind of approximation?
Generally, no. It computes it exactly. That's why you have these built-in functions. And if you recall the way we implemented it, I used whatever, some tensor of exp and so on. So all of these are built-in functions within Pytorch itself. So for those functions, it can compute the gradients exactly, at least to whatever precision can be provided. Right? So it's not doing numerical differentiation. It's using the derivatives of those functions explicitly. Right. Right. So in the previous class, we trained a simple logistic regression model. Let's now train a neural network model along the lines of what you can typically use. So essentially using all of the features that are available in the Pytorch library. So in the last class, we explicitly wrote down the gradient descent step, but we only used Pytorch to compute the gradients. And we explicitly wrote down the computation of the loss function and so on. But a lot of the time, people usually don't do that because all of those are already built into Pytorch. And there are also reasons why you don't want to do it in practice, because Pytorch has other ways of handling numerical and precision issues. So, for example, when you have loss functions, we sort of implemented the softmax or the logistic loss explicitly, but then there are more numerically stable ways of doing it. Remember that all of these involved exponentials and logarithms, and exponentials can blow up and so can logarithms, right? So you have to be a little careful in how you evaluate all of these quantities, because particularly when you're doing gradient descent, just because of numerical precision issues, the algorithm may not converge. Right. So under the hood, Pytorch can do all of that for you, and we'll just quickly see how to do that. Okay. So I've already written down code for this, and this is in a way very similar to what we have done in the previous class. But I'll just walk you through what are the main steps. Okay. So as before, you just declare whatever libraries you want. And in particular, we'll be using the torch.nn library for declaring neural networks, because our goal now is to train a simple neural network with one hidden layer. Right? And we download the training and test data. And the first step, as we did in the logistic regression case, is to define the neural network or define the model itself. Okay, so this is our hypothesis class, and our hypothesis class will consist of neural networks with one hidden layer. The input to this neural network is an image, which is a 28 by 28 image, and I'm going to define a neural network with 512 hidden neurons. Okay, I've just chosen that arbitrarily. I could choose it to be something else. It is not going to change things significantly, right? In fact, if I go down from 512 to something much smaller, the number of parameters decreases, and in fact, you'll have better convergence properties. All right. So for the hidden layer, I'm using a ReLU activation function. Okay. For the output layer, also I'm using a ReLU activation function. Right. So the whole definition of the neural network consists of I'm defining the sequence of operations that need to be performed by the neural network. So there is first a hidden layer, followed by a ReLU activation, followed by another hidden layer, a ReLU activation, and a final linear layer. So each linear layer is just a matrix multiplication and a bias. All right. So the class neural network consists of two parts. First is the so-called definition of the architecture, what pieces put together form the neural network, and another function which tell you what to do. All right. So this basically says that given an input x, you first flatten it, which is if you have a 2D vector, then you convert that to a 1D vector, and then apply this self dot linear dot linear ReLU stack. All right, which means just apply these in sequence and then return the output. Okay. Now a side note is that I've instead of putting all of these layers within one stack, all right, I've defined nn.sequential, which means apply these sequentially. I could split this into two parts. I could say that self dot stack 1 and self dot stack 2, and then apply stack 1 followed by stack 2. Now, cosmetics aside, there are also advantages of splitting them into two parts. And one of the reasons why people primarily split into multiple parts is when let's say you want to retrain on a different data set, or you want to fine tune only some of the layers, then you could do so by saying that only these set of layers or this stack has to be retrained and everything else has to remain as it is. So if I define this stack in one go, then when I do the training, it is going to train all of the weights in this entire stack. And if I want to train only certain layers and leave the rest and freeze all of the weights of the rest of the layer, then I can do so by splitting them into two and then explicitly mentioning that only this part has to be trained. Right? So that is particularly useful when you try to build bigger models or more complicated problems. Okay. And as I mentioned earlier, all of this, whether it's the weights, activations, gradients, all of these have to live within some particular device, which is either the GPU or a tensor processing unit or your CPU. By default, it is going to be the CPU. And here, in this case, I only have a CPU. I'm not able to load it onto a GPU, so I will load this onto the GPU. Right? Let's see. So this defines the neural network or instantiates the neural network. The second line essentially just defines what the loss function is. So it's just a single line. There are, again, built-in loss functions within Pytorch, and you can use them as it is. But there are also ways where you can define your own fancy loss function and use that as well. Okay. The main advantage, as I mentioned earlier, of using Pytorch's default loss functions is that all of these are going to be implemented in numerically stable ways, and there are other optimizations that are done so that you can both evaluate as well as like do gradient descent and so on efficiently. So in practice, I mean, outside this course, when you want to do things in practice, it's always better to use the functions that are provided by the Pytorch library than implement things on your own. Okay. And you can also specify what optimizer to use. In this case, I'm using stochastic gradient descent. and I'm using a learning rate of 10 to the minus 1. I can change the learning rate. There are a bunch of other parameters. The best way to learn about all of these is to go through the documentation within Pytorch itself. So there are only a small number of pieces to this entire code. So I would encourage you to go through the documentation, see what all are available, what all parameters you can tweak. Right. So for instance, just by hovering around here, I can see that the class SGD can take a bunch of parameters, including like momentum and dampening and weight decay and so on and so forth. There are a bunch of other parameters that you can specify. We'll see what some of these parameters are in this class and the next. What, for example, momentum means. And Nestero is a word that you've already seen previously when I talked about accelerated gradient descent. This basically, Nestero essentially says that you want to do accelerated gradient descent. It's by default set to false, which means that you do vanilla stochastic gradient descent. So for this particular experiment, I'm using a batch size of 64. In fact, let me perhaps reduce the number of hidden neurons from 512 to maybe 100. Let's just restart. In fact, all of this code is available in the Pytorch website itself. I'm just using that and nothing fancy. Okay. Now, having defined the loss function and the optimizer, we are also going to use this data loader, which is another feature that is available provided by this torch.utils library. And what the data loader essentially does is it provides additional functionality that allows you to train using stochastic gradient descent or any other optimization algorithm. So for example, you just have to specify what your data set is and what batch size you want to do, and whether in every epoch you want the whole data set to be shuffled or not. I could just set shuffle equal to false, which would mean that in every epoch, I'm using the data in that particular order itself. It's not going to be reshuffled. If I set this equal to true, then in every epoch, it is shuffled independently of the other epochs uniformly at random. And the data loader essentially provides the data in batches equal to the batch size. All right. So once we have all of this, and so in the test loader, for example, I've set shuffle equal to false because I don't need to shuffle the data every time I'm testing it. I'm not going to use it for gradient descent, so it doesn't make any difference whether I shuffle it or not. I'm just going to evaluate the accuracy over the entire test data set. So once we have this, we want to train and then test. So there are two functions to do precisely this. So first, so n is the total number of, I think I'm not using it, but the n is the number of points in my data set, in my training data set. So first, I'm saying model.train, which kind of instructs Pytorch that within this function, I'm going to use it, I'm going to train the neural network. This outwards, it doesn't do anything, but internally, it sets some of the parameters within the automatic differentiation to sort of instruct it to that, okay, some of these gradients are going to be used in gradient descent or some kind of an optimization step. All right. So then you have this iteration. So every time you call the data loader. So what the data loader does is essentially provide the data points in batches. So this batch corresponds to the batch number, and X and Y correspond to one particular mini batch of inputs and outputs. And yeah, so the first step is, again, you have to load both X and Y to the device, which is your CPU or GPU. Now, in general, if you're just using the CPU, this doesn't provide any added benefit. But when you're using the GPU, it's always advantageous that you have to put everything to the device, so that processing can become faster. So first, now that everything is loaded in, you run the forward pass of back propagation. So you evaluate the model and then you compute the loss. Right? And while you're doing this, the Pytorch library is in the backend it's developing the computation graph to run back propagation over. And this single step, loss.backward, computes the gradients, all right, using back propagation. Now, when we did logistic regression, if you recall, we explicitly wrote down the stochastic gradient descent steps as whatever W equal to W minus the learning rate times the gradients. In this case, I don't need to call out the gradient separately. Just doing optimizer dot step is going to run all of those equations without me having to write them out explicitly. Now, in stochastic gradient descent, it doesn't save much space because anyway, it's just a one-line step. But when you're running more complicated optimizers, this simplifies things. And once you run one step of stochastic gradient descent or whatever optimizer, you must zero out the gradients so that in the next step, you're doing things from scratch. Essentially, you're saying, okay, this is the end of the computation graph. For the next time, you have to rebuild the computation graph from scratch. All right, and then I'm just saying that for after every 100 batches, print the current loss. Right. Okay, and similarly for the test function, I'm just evaluating the performance. And as we did in the case of logistic regression, evaluation for over the test data set is done within a block which has torch.nograd, which instructs the Pytorch library that all of these instructions are not to be used to build the computation graph. All right. Okay. So you can run this. It's going to take a little bit of time because obviously there are many more parameters to optimize over compared to a simple logistic regression case where we had just one layer. So using this, at the end of the first epoch, I'm getting an accuracy of roughly 80 to 83%, which is roughly the same as what I got when we are doing logistic regression. So although I've increased the size of the neural network and I'm paying a much bigger price in terms of compute, I have not really gained much, right? I just terminate the execution for now. But Let me make one more change wherein I'm doing nothing else. Okay, so maybe another experiment I'll try to run is I'll decrease the learning rate. Okay, because I chose this learning rate 10 to the minus 1 based on what I did for logistic regression. I used roughly the same learning rate over there. But what happens if, say, I set a learning rate of 10 to the minus 3? What would you expect to happen? Would you expect to see roughly the same accuracy, higher accuracy, or a lower accuracy?
No.
A lower accuracy, and why?
Takes lot of time to come.
Sure. I mean, we didn't explicitly see that, but you're essentially right. As it turns out, we will see that it doesn't converge to a local optimum. It takes a longer time to converge, and reducing the learning rate has precisely that effect. Right? The accuracy just dropped to 31%. Okay, and you can also see that the training loss has not decreased much. It started with around 2.3 and then went down only to 2.24. Right. One thing to keep in mind is that we are running stochastic gradient descent. It's not a strictly a descent method in the sense that in every iteration or every epoch, the loss is not guaranteed to strictly decrease. It will fluctuate by a little bit. Okay. Okay, great. Let me not run this any further because I'm not going to get anything much out of it. So then what's the solution? What do we do? Is there a better way of approaching things? Because in the end, I need to choose the learning rate, right? So one way to choose the learning rate is to set that as a hyperparameter. You have a validation set, and then you vary the learning rate and see which choice of learning rate gives you the best performance. And that's one of the approaches that is typically used. But another approach is to look at the optimization algorithm a little more carefully and see if the optimization algorithm itself can be adapted to give you a better performance. And that's what we will explore in this class and the next. All right. So just to give a sneak peek, what I'll now do is change the optimizer from SGD to another variant, which is called add. I'm using the same learning rate. Nothing else has changed. You can see that the loss has now dropped from 2.29 to 0.92. So I encourage you to play around with this code a little bit, see exactly how the loss varies with different choices of optimizers, different choices of learning rates, and so on. Right now, you can see that the loss is not strictly decreasing. It went down to 0.4, then went up to 0.6, and now is around 0.3 something. Right, so I'm back to an accuracy of 83-ish percent. right? With the same learning rate of 10 to the minus 3. Okay. So in some sense, I can redo this with a slightly different learning rate. So let's say I choose a learning rate of 10 to the minus 2. Let's see what happens. Again, for now, let's just focus on how the loss varies. It's still dropping significantly. It's not too bad, right? I've increased the learning rate from 10 to the minus 3 to 10 to the minus 2. But now the loss is actually a little higher. Of course, this could be for two reasons. One is the choice of learning rate would be bad. The other is, of course, there's randomness in the algorithm. So it's just that I go through a bad patch. Okay, that's also something you have to keep in mind. Because you're doing stochastic gradient descent, every run is going to give you something that's slightly worse or better. But the loss is still roughly around what it was at the end of the first epoch with learning rate into the minus 3. It's going to around 0.4. Accuracy is still roughly the same, 83%. Okay, so although I've changed the learning rate quite a bit, the accuracy has not changed significantly. Okay, so in some sense, it's slightly more robust to the choice of learning rate than gradient descent or stochastic gradient descent. So let's look at some of these uh, algorithms for optimization. That's going to be the agenda for this lecture and the next. So again, let's recall the stochastic gradient descent algorithm. In SGD, what we're basically doing is we start with an initial point W0, and then in each step we run the following. We set WT minus T plus 1 to be equal to WT minus the learning rate times the stochastic gradient, where again we're assuming that the stochastic gradient is unbiased. Okay. In practice, of course, you're going to do it with random shuffling, so this property is not strictly satisfied. But at least for the purpose of analysis and definition, we'll assume that this is unbiased. Okay. Keeping in mind that in practice, we will use it with shuffling. So going back to the question, how do you choose the learning rate? So far, we've chosen the learning rate to be constant in the experiments that we've run, but there are other ways of choosing the learning rate itself. And a very common or practical approach is to use a learning rate schedule, which is time dependent, but it's fixed beforehand. Okay. So, for instance, in the analysis of stochastic gradient descent for non-smooth objectives, we set a learning rate that decayed as 1 over square root of t. Right? So that's something that is typically done in practice. You set the learning rate to be some constant divided by t or some constant divided by square root of t. That's a very common approach to use. But there are other heuristic ways of choosing it as well. One common approach is the step decay or what is also called a multi-factor scheduler, wherein the trajectory of rho t looks something like this. You start with some constant, leave it to be that constant for a certain number of iterations, but after that, you decrease the learning rate by some specific value. So this is the value of rho from 1 up to some capital T. And then for the next T time instance, you decrease this by some particular factor, and so on. So it's piecewise constant and decreasing. That is one common approach. Another common scheduler that is used is the cosine scheduler, where instead of keeping it constant and decreasing it to a specific value all of a sudden, you let the um, scheduler decrease the learning rate in a much more gradual fashion. And in fact, like a cosine. So if you plot the trajectory over here, so rho t will look something like this, and then a constant. So this is t equal to 0. This is at t equal to some capital T, which is fixed beforehand. And beyond that point, the learning rate is fixed. So this is another scheduler which seems to work well in practice. Okay. All of these are just heuristic ways of choosing the learning rate. Right. But as we've seen, if you just run stochastic gradient descent, the convergence rate is sensitive to the choice of rho t. In fact, even when we did the derivations and I gave those bounds on the rate of convergence of stochastic gradient descent for different classes of objective functions, we got those bounds only by selecting the learning rate to be some specific value dependent on B and L and all of those other parameters, right? But in practice, we don't know what those quantities are. So if the function is L smooth or mu strongly convex, we don't really know mu or L in most cases. So typically, you either choose the convergence, you choose the learning rate in some ad hoc fashion, or you use it using a validation set. Another point to keep in mind, something that goes back to our analysis of gradient descent, is that the convergence rate depends on the condition number of the Hessian. Right? When we analyzed the strongly convex and L smooth case, we saw that the rate of convergence depended on the parameter L divided by mu for a function that is L smooth and mu strongly convex. And these parameters happen to be bounds on the eigenvalues of the Hessian. This was greater than or equal to mu and less than or equal to L. Right, for every point W. So if L and mu are close to each other, that is the condition number L by mu is close to 1, then convergence is fast. If not, the convergence can be very slow. And the reason why you have this, why the condition number plays such a role, can be seen from the geometric interpretation of the eigenvalues of the Hessian. So what does the Hessian give us? It essentially tells you how the curvature of the function is, whether it's steep or it decreases in a very gradual manner, right? And if the eigenvalues are roughly the same, that is, this condition number is very close to 1, then it means that the curvature is roughly the same in all directions. So a constant learning rate tailored to the choice of L and mu can get you to the point of minimum from any point. You start with any arbitrary point. You can choose the step size appropriately to reach the point of minimum fairly quickly. All right. So let's note that down. So let's say that I have lambda min and lambda max. So this particular ratio tells you how much . the curvature of the function differs in different directions. And because we're choosing a learning rate, if you choose a learning rate that depends on the steepest curvature, then it means that if you choose the learning rate according to that and you tend to move the along the direction where the curvature is lower, then you take a very long time to converge. But on the other hand, if you choose the learning rate that is tailored to the curvature of the gradual uh, descending direction, then it means that you may oscillate when you're in areas where the curvature is much steeper. Okay? Now, the curvature is different from the gradient itself, all right, which determines the descent direction. So this is a second order derivative property and not the first order property. All right. And one of the main reasons why we are stuck with this particular problem, with this dependence on the Hessian or the, the condition number, is because we are choosing a fixed learning rate. So irrespective of which direction you go to, the amount of step that you take only depends on the gradient and how you chose the learning rate beforehand. We're not really making use of the second order properties of the function itself, which is the curvature. So can we improve this? And in fact, there is a way of improving this using a second order method, which is Newton's method. So Newton's method is the following. Again, as in gradient descent, you initialize W0 and then for t equal to 1, 2, up to, I guess in this case, 0, 1, 2, up to t minus 1, you set Wt plus 1 to be equal to Wt minus the Hessian evaluated at Wt inverse. Remember that the Hessian is a d by d matrix times the gradient of f evaluated at Wt. Right? So this is some matrix. Let's call this H inverse So let's run a simple experiment to do, again, logistic regression, but with only two parameters. Okay? So basically, I have a binary classification problem, and the output is simply sigmoid of W transpose X, where X is a two-dimensional vector. W is also a two-dimensional vector. And the loss is measured using the cross entropy loss. And I have functions that evaluate both the gradient and the Hessian. So I'm generating a random data set of 10 points. And this is the ground. The ground truth is basically equal to 1 if the norm of x is less than a certain value, and it's equal to 0 if the norm is greater than some particular value. In this case, I think it's 0.5. All right. So this is a plot of the loss function as a function of W1 and W2 because they are the trainable parameters for my model. It turns out that this is a nice convex function. But the curvature is not really the same in all directions, as you can see. Okay? And that is what we'll make use of in the rest. So let's not worry about the rest. So I'm running gradient descent for 60 steps, stochastic gradient descent also for 60 steps, and the Newton's method only for 15 steps. Let's ignore the rest of whatever is Adagrad or RMS prop or Adam for now. But you can see that, okay, so Newton's method seems to give a much higher loss for some reason. Okay, some reason Newton's method, something's wrong with Newton's method perhaps, but anyway, let's see how they behave. Yep. Yeah, I suspect it was just because I was doing some out of order execution over there, which messed up things. But yeah, so this is the trajectories of three of the algorithms: gradient descent, stochastic gradient descent, and Newton's method. So we started with this initial point over here, and gradient descent, as you can see, is moving smoothly towards the point of minimum, which happens to be over here. But in 60 steps, it hasn't really gotten close to the point of minimum. On the other hand, stochastic gradient descent is, because it's a stochastic method, it jumps around quite a bit, but eventually it doesn't do much better than gradient descent itself. Right? Newton's method seems to be fluctuating a lot more wildly, but it's actually getting closer to the point of minimum. All right. In fact, I can try to increase the number of steps to, let's say, 25. I get a loss of 0.63, which isn't too far from the actual minimum itself. All right. I think the minimum is around 0.58 or something that in this particular case. Okay, so even though the Newton's method seems to be fluctuating a lot more widely, it actually gets to the minimum point much faster. So what is happening over here? Why is Newton's method performing so much better than gradient descent or stochastic gradient descent? Um, so one way of intuitively looking at Newton's method is that this H inverse is doing some form of conditioning, in the sense that it's adapting. It's firstly, it's also changing the directions along which you move. In every step, you're not moving in the direction of steepest descent. It's not moving in the direction of the negative gradient. It's moving in a slightly different direction. But also, it's adapting the learning rate differently in different directions. And in a sense, that's, if you had to improve gradient descent, that's the first thing that one can think of. The problem with the gradient descent and its slow convergence is because if you choose a particular learning rate, then if it's too small, then along the directions of slow curvature, it's going to decay, or it's going to converge very slowly. If you choose a large learning rate, then along regions where the curvature is very high, you'll keep oscillating. Right? So a slightly better way to do it would be if you can choose the learning rate for regions of low curvature, you choose a larger learning rate, so you take a bigger step. For regions where the curvature is high, you choose a smaller learning rate so that you don't oscillate. Right? And that's really the intuition behind many of these adaptive methods for stochastic optimization. You try to choose the learning rate appropriately along different directions, but also in a very data-driven manner. Okay, so we have this Newton's method, which seems to perform very well. All right, it converges much faster than stochastic gradient descent or gradient descent. Why not just use Newton's method in practice? Yep. So the biggest problem with Newton's method is, well, first you have to compute the Hessian. So you need to compute the second order derivatives, which has an added complexity in itself. But it's not just enough to compute the Hessian, you also have to compute its inverse. And if it's a d-dimensional, so if W is in Rd, then the Hessian is a d by d matrix. So inversion requires order d cube time to invert. And for a reasonable model which has like a million parameters or a billion parameters, that's practically not possible, right? but then we still want to get this nice feature, right? So can we do something that mimics this operation by H inverse? Okay, so this is sometimes called a preconditioning step, or a conditioning step, where you condition the gradients in a particular manner, right? Depending on the curvature. So this uses the second order derivatives, but is there a way of choosing, instead of a H inverse, some A inverse, which can be computed efficiently, but also has the added effect of um, improving the rate of convergence? So basically, instead of running the standard gradient descent, what we want to do is something similar to this. So Wt plus 1 is equal to Wt minus maybe some learning rate rho times A inverse At inverse times Wt, or gradient of Wt. More generally, we'll just use f prime of Wt, where this f prime can be a stochastic gradient. Um, Note that the standard gradient is also a valid stochastic gradient. It's equal to the gradient with probability 1. So standard gradient descent is just a special case of stochastic gradient descent. So this f prime can either be the true gradient itself, or it can be a mini batch stochastic gradient. So for any reasonable matrix A, inverting it is going to take computation time dq, right? Uh, but for what choice of A can we bring it? So we ultimately we want computational complexity that depends, that grows not more than linear in D, right? Because after all, we went through back propagation. The main motivation for using back propagation instead of doing numerical differentiation was that numerical differentiation had computational complexity order D square, whereas back propagation only takes computation time order D. Right? So we really don't want to go beyond order D. So what choice of matrix AT, or what structure on matrix AT would give you inversion time which is linear in D? Diagonal matrix, right? So in particular, we will want AT to be diagonal. But AT can potentially depend on WT and possibly even the entire history of WTs. So the first so-called adaptive gradient method that we'll see is called Adagrad, which is adaptive gradient. And it basically makes use of this particular intuition. So Loosely speaking, we want to choose our step sizes or learning rates such that if the magnitude of or essentially if the curvature is high, then you choose a small step size. The curvature is slow, then you want to choose a slightly larger step size. What the adaptive gradient method does is, instead of doing that, it looks at the accumulated energy of the gradients along different directions and chooses the step size based on that. So let me say that if, let me use this particular notation, let's say the vector bt is equal to the gradient or stochastic gradient at time t. Okay, so I'm just using bt to denote this particular quantity. And I'll say that st is essentially the accumulated energy along each of the components up to time t. So it's equal to summation t prime equal to 0 up to t of bt square. Again, when I'm doing this operation bt square, I'm essentially using the Python or NumPy notation in that each component is being squared over here. Right. So basically, the ith component of st is summation t prime equal to 0 up to t of bi t prime square. Or equivalently, I can also say that st is equal to s t minus 1 plus bt multiplied with pt, okay, component wise. So in each step, if I have to compute this st, I don't have to pay much of a price because I just have to store st minus 1 and then multiply it with um, bt squared. So per iteration, it's just an order d computation. And I'll set a vector at to be equal to the square root of st plus a small parameter epsilon, where this epsilon is some very small number. Take it to be like 10 to the minus 6 or 10 to the minus 7 or something like that. Okay, and again, this square root is also a component twice square root. And your matrix A or AT is just the diagonal matrix with entries AT. And that's it. That's the Adagrad algorithm. So just to summarize, you basically do W t plus 1 equals Wt minus some rho divided by S square root of St plus epsilon times Bt. So this two sets of equations gives you the entire Adagrad algorithm. Again, I'm using the notation that something divided by a vector is done component wise, okay, following the standard NumPy notation. All right. Uh, in fact, what you can prove is that the Adagrad algorithm is going to converge at least as fast as gradient descent. And empirically, in many cases, Adagrad performs better than standard stochastic gradient descent. But our primary focus will not be on Adagrad itself, but rather on improvements to Adagrad. We see that there's a big flaw to the Adagrad algorithm. Okay, but even before that, what's really the motivation? I just introduced this choice of um, ST without giving any intuition as to why I'm choosing it or where this equation came from in the first place, right? And one way to look at this, again, I will not prove this, but you can show that. Sorry, let's recall our goal. Our goal in any learning problem is to minimize some empirical risk. So the intuition, the very high level intuition behind designing an algorithm like Adagrad is the following. Suppose we have reached, let's say, the tth iteration, and we want to decide what to do in the t plus 1th iteration. Sort of a greedy procedure where you take optimal local steps and hope that it works well globally. Right? So what? Let's say I already have W. I want to choose a Wt plus 1, which is equal to Wt minus A inverse times Bt, right? Or At inverse Bt. And I want the best, the choice of At inverse that minimizes the overall empirical risk. So that's a reasonable way of choosing AT. If I'm doing something optimal in every step, then overall I'll be performing well. Now, doing this minimization directly turns out to be much more complicated, because if we could do this, then we might as well solve the original optimization problem itself, right? So instead, you try to approximate this in some particular fashion and see how that can be minimized by choosing AT. So what you can show is that Rs of W minus Rs of W star, where W star is the minimizer for Rs, is upper bounded by W minus W star. Let me call this Rs of Wt, Wt minus W star. I'll let you know what this norm subscript A means. Plus, sorry, there should be a row here. This is 1 by 2 rho plus rho by 2 summation t equal to 0 up to t minus 1 of bt norm squared subscript A inverse. Where this norm square subscript A essentially means X transpose AX. Okay. So this particular quantity is simply Wt minus W star transpose A Wt minus W star. This quantity is Bt transpose A inverse Bt. Okay. Now, minimizing this whole quantity would amount to minimizing Rs of W. But if T is sufficiently large, then it turns out that this quantity dominates, because this is the only T-dependent parameter. You can show that this quantity is always going to be bounded, assuming that the objective function is sufficiently nice. And if you minimize the second quantity, then basically that subject to the constraint that A is a diagonal matrix, then that just gives you the Adagrad rule. So the second term, if you stare at it carefully, it's rho by 2 summation t equal to 0 up to t minus 1 of 1 over, also put summation I equal to 1 to d bi t square divided by ai. Because this A inverse is a diagonal matrix, which has diagonal entries 1 over ai, and what you have over here is bt transpose A inverse bt, and the norm square just happens to be bit square times ai divided by ai. That's it. right? So therefore, the goal now is to simply minimize this particular quantity, right? Now, if there are no additional constraints, then minimizing this is a trivial task because I can just set AI to be something very large. This quantity can be made arbitrarily small. So you have to impose an additional constraint that the total energy of the A matrix is bounded. So you impose the constraint that summation whatever AI mod AI is less than or equal to alpha. Maybe AI square is less than or equal to alpha. Just to ensure that this matrix A has bounded or A inverse has bounded now. So I think this should be 1 over AI square should be less than or equal to alpha. Yeah, just AI square should be less than or equal to alpha. Okay. So subject to these constraints, minimizing this essentially just amounts to choosing AI to be some constant times summation t equal to 0 to t minus 1 bi square. So this is equivalent to minimizing summation I equal to just rearranging the order of summation. This is summation t equal to 0 up to t minus 1 bi t square divided by AI. And the numerator is simply S. Yeah. So the numerator is simply SI T. And you can show that that essentially amounts to choosing AI to be square root of SI T, assuming that all of these SITs are positive, because otherwise you can't really divide by, otherwise you'll get a divide by 0. So some constant times, this is proportional to SIT depending on this energy constraint that you impose. Any questions?
Once the thing that today we could be diagram matrix the complex technically. There's some other way for us to arrive at A to B diagram. I'm doing it.
So is the question whether, so let's say I have this general conditioned gradient descent or stochastic gradient descent. Is the choice of A to be diagonal optimal? Is that your question? In the sense that, is there any advantage in choosing A to be a non-diagonal matrix?
Complex.
Apart from complexity, not really. Complexity is really the main reason why you force AT to be diagonal matrix. Otherwise, it's always advantageous for you to take it to be non-diagonal.
Just sort of people like AT is there and here.
Correct, because we're enforcing that particular constraint. That's how I arrived at this optimization problem over here. This is assuming that AT is a diagonal matrix. If not, this is not the optimization problem you should be looking at. Okay, and this choice is optimal. I mean, firstly, this does not minimize the risk itself. It only approximates. It only approximately minimizes the risk for sufficiently large t. Because it only approximately minimizes this quantity, and that too only if this second term is much larger than the first term. You're kind of ignoring this first term completely.
So that this somehow translate to because that's the idea.
That view is not obvious in this particular case. In fact, there's a different way of deriving this entire procedure. This intuition that I have provided over here is one way of looking at it from the ERM perspective. But in fact, you can view this as a specific instance of a more general class of optimization algorithms called mirror descent. So this is a special case, or in some ways it can be seen as a special case or a specific instance of mirror descent. So mirror descent is a general class of descent algorithms, and depending on the so-called divergence that you associate with mirror descent, a specific class, a specific choice of divergence translates to this Adagrad algorithm being mirror descent with that particular divergence. So if you've seen mirror descent before, then it can be viewed. If you've not seen mirror descent before, don't worry about it. But essentially, the derivation of the Adagrad algorithm is not really from this perspective. It comes from totally different roots. Okay. But one of the main challenges or one of the main problems with the Adagrad algorithm, you can see it from this particular step. Now, what are you doing in every step over here? You're accumulating energy, right? So as the number of steps becomes larger and larger, the total energy accumulated will also grow, right? Which means that after a reasonably good number of steps, the denominator becomes very large. All right, so then you stop taking any further steps. Right, and that's one of the main problems with the Adagrad algorithm and implementing it in practice. So let's go back to our experiment over here, and let's also plot the trajectory of the Adagrad algorithm. It's not entirely clear over here, but you can see that this orange trajectory corresponds to SGD, whereas the green trajectory corresponds to the Adagrad algorithm. And you can see that initially it was taking slightly longer steps, because the step size also depends on the curvature at that particular point and also the stochastic gradient that you picked at that particular time instant. But as you go over here, you can see that the step size taken by Adagrad is very, very small. And that's the main challenge. You can't run Adagrad for beyond a certain number of steps, because beyond that particular point, the step size becomes very small, because you've accumulated too much energy until then. So a simple way of improving Adagrad is using this algorithm called RMS proper. So the RMS prop, what it essentially does is, well, you instead of accumulating all of the energy up to this particular point, you make use of some of the energy that you've accumulated, but then you sort of give a decay rate, or you don't emphasize the energies of the points that were too far behind in the past, right? So essentially, instead of saying that ST is equal to ST minus 1 plus BT square, you do some this ST equal to beta times ST minus 1 plus 1 minus beta times BT square. Where BT, remember that BT is the either the gradient or the stochastic gradient in the Tth time step. Right? So this is sort of a damping or a forgetting factor. So for example, the term corresponding to B0 would be weighted by b to the power t minus 1. So if you look at this more carefully, then ST is equal to beta times S t minus 2 plus 1 minus beta times S b t minus 1 squared plus 1 minus beta times bt squared, which is beta square S t minus 2 plus 1 minus beta times bt minus 1 squared plus 1 minus beta times bt squared. So in general, this is equal to beta to the t prime S t minus t prime plus summation, let's say j equal to 0 to t prime minus 1 of 1 minus beta times beta to the j b t minus j square, right? So terms that are far behind in the past get multiplied with beta to the j, and if you choose beta to be something less than 1, then it's being multiplied with a much smaller quantity. Right? So that's one way of controlling the energy. That is, you give importance to the recent history of the gradients, but then you forget what happened too far behind in the past. And if we look at the trajectory of RMS prop, it in this particular instance, it varies a lot more widely, but it actually gets you closer to the minimum than stochastic gradient descent or even Adagrad. Okay, and this is because the step size is much larger because you don't have so much of a decay. In this case, okay, so here there's another quantity, right? I should say that the overall, the effective learning rate is rho times 1 over square root of st minus 1. So essentially you would run in every time step wt plus 1 equal to Wt minus rho divided by square root S T plus epsilon times Pt. Right, so this is the effective learning rate. Your choice of rho also determines how large the step size you take. Okay. All right. Any questions? So what you can show is that, okay, I'll get to that later, but maybe this is a good place to stop. In the next class, we look at another algorithm which improves upon both Adagrad and RMS problem.